Hi children, all of you staying home and staying safe, right? So if you are staying in home for a long time, what is the next thing we'll be doing is nothing but we must be busy with our gadgets, and we'll be checking with all the important updates. So in today's session, what we are going to do is nothing but about current electricity, that is the current with which you're going to charge all your gadgets and you're going to use them. So basically, without the current, what is the quarantine we have now? That is not possible for us, as well as without our gadgets, right? So how this current electricity is going to be useful for us, we know that very well, but how it works, what are the basic steps behind it, that is what we'll be doing with today's session. Before getting into the current and electricity, we will be doing a small thing with physics, which is the normal thing what you used to do in your day-to-day life, with which you could able to have a fun, right? So like the last class, what is the thing we have done with the small ball and the water, a small magic, the similar kind of thing we are going to do here. It's also kind of magic, but there is a physics behind it. What is that? Let's look into it. Okay, so what I'm going to do in today's session, that is the small fun or magic, is nothing but with the egg. What we'll be doing normally with the egg, or when we are seeing an egg, what will come into our mind is nothing but so many different type of food what we could able to have or make with the help of the egg, right? So we are not going to do about it, we are going to do something else about it. And this is the experience what all of you must be having by mistake, or you would have been break an egg and you would have been got scolding from your parents, right? So about the same thing only we are going to do about it. Now you're going to drop an egg and the egg is not going to get break. See how nice it is, right? Normally whenever egg is going to fall, it is going to get break. What is the reason behind it, how to avoid it, that is what we'll be doing with today's session. So to do that one, you're going to take a small ball like this, air filled ball like this, and you're going to cut it open. You're going to fill that ball with the popcorn, and you're going to place the egg in the middle of it, and you must seal it so firmly with the help of the cello tape, right? And what is the next thing you're going to do is you're going to take that and you're going to reach a height. It may be your balcony or somewhere else, which is going to be at a higher height, and you're going to throw that and you're going to drop this ball from that height. So if you're going to drop or throw it, what will happen normally? Yes, obviously all of you know that what will happen, the egg will get break. So what is the thing begin, that is nothing but whenever the egg is going to fall, that means that we all know that when the egg is going to be on the floor, or when it's going to be in your hand, that is at the floor level, the energy associated with the egg is going to be the potential energy. So it will be having a potential energy when it is going to reach a height where you're going to take the egg. Due to this height, we all know that potential energy will be given by the formula mgh. So due to the height, it will be having a higher potential energy, and when you're going to throw it, or when it's going to fall down, all this potential energy, or most of the potential energy, will be converted into the kinetic energy. So during the fall, what is the velocity the egg is going to have is going to be given, that is going to be associated with the kinetic energy. But there is one more energy as well with all these pieces are being associated with, which is nothing but who are all interested in chemistry as well as who are all learnt about the nuclear physics must be aware of this binding energy. What do you mean by this term binding energy? The amount of energy required for the particles to be bounded together. If it is a nucleus, we will be calling that as nucleus and the nuclear particle, nuclear binding energy. Generally, it's going to be the energy which is binding the particles together. So that's the same thing we're going to have here as well. There must be a binding energy associated with the particles by which the eggshell is made up of with. So that binding energy what we are going to have, that will be, for example, that is going to be of 10 joules, and the kinetic energy is going to be of 15 joules. Obviously the eggshell is going to receive a higher energy from the outside. This higher energy will be creating a higher pressure outside the eggshell, so that it will get break. What we are going to do exactly, or what we are trying to do exactly by covering all this with that popcorn stuffs, is nothing but what is the excess kinetic energy is going to be received because of the fall, that is going to be received by the popcorn and the surface of them. So as a result of it, when the egg is going to reach the ground with that popcorn ball, then the binding kinetic energy what it is going to have in the outside is going to be less than the binding energy of this eggshell, which may be 8 joules, so that obviously the egg will not break. You can try that out and then you can check with this. This is how physics which breaks the egg will also save the egg from breaking. Okay, so what is the next thing we are going to do is current and electricity, I said, right? So within the current and electricity, when we are trying to learn about current and electricity, without 3 terms we will not be able to understand this chapter fully. What are those 3 terms? Is nothing but current, voltage and the resistance. All of you must be getting a feel that you have been heard about it somewhere, right? Yes, it's very correct. You have learnt about that in your 10th standard. Anyways, we are going to do a recap and I'm going to give you a clear idea about what all these 3 and how they are going to be connected and what we are going to do with them in this 12th standard portion. Okay, so first, when the current electricity, or when we came to know about the electric charges, is nothing but by seeing this only. That is, by seeing the lightning only, we came to know that we do have a source which could able to give the light except the sun. Okay, so the person or the scientist who was working on it and who have done so many experiments based on this and got the name as mad is nothing but Benjamin Franklin. So the famous kite experiment of Benjamin Franklin you must be aware of, right? So if you're not aware of it, I will just give you gist about it. He was holding a kite which is made up of with silk as well as a silk thread, and it is being joined with the key associated with that. When he made the kite to flew so closer to the clouds during the rainy time or during the thunder or the light during the thunder time, the kite received, as the silk is a material which will be coming under the triboelectric series, it will be able to grab the charges easily, so that it's grabbing the charges from the cloud and it's giving him the highest amount of electric current. But the amount of electric charges which is received by this setup is going to be non-uniform based on how much amount of charge is going to be received, or the climate, or all the other stuffs, right? But this is not electricity. Just the flow of electrons are not going to be the electricity. The electricity or electric current is nothing but even flow of, or a steady flow of electric charges. We have been seen when the water is going to fall from a dam, which will be non-uniform, but when it is going to fall through a pipeline, it will be a uniform one, right? So if you're going to have a uniform flow of electric charges, that is going to be called as the electric current, right? So that's what the same thing we are going to do. But whenever we are talking about the electric current, we always used to talk about something called as conductor. We always used to talk about something called as conductor. What does this conductor means, or which makes a material, normal material, as a conductor? That's what we are going to do, because whenever we are talking about atom, all the atoms are going to have a nucleus and they will be having the electron. If all the materials are going to have the nucleus with a positive charge and the electrons around them, then which makes only few of the materials to be named as conductor. Only few of the materials which is being named as conductor. What is the reason only we are going to do in today's session. So what is that is nothing but, as you are seeing over here, the electrons are moving from one atom to another atom. They are having a continuous flow over there. And if you are going to look at it over here, you are having a past like a red color which is highlighting and it's keep on moving, right? You can take that either in terms of this battery thing, or you can imagine this as the room temperature what you're going to have. When we are talking about the room temperature, as I told you, all the materials are having the nucleus as well as the electron, but only few of the materials, that is what we call as a conductor, those few of the materials are only having the capability of releasing their electrons at the room temperature. What do you mean by this term room temperature? Is nothing but when we are talking about this term room temperature, the room temperature is going to tell us that there is an external supply of energy to the material. That external supply of energy is more than enough for the atom to liberate its outermost electron and to leave it in the freely movable state, which will be called as free electron. So this is the reason why the metals are called as the conductors. What is the room temperature? Or the room temperature heat energy is available, that is more than enough for the metals to leave or allow their electrons to circle around inside the material but out of the atom, which makes the electric current as the possible one. Now, if the electrons are going to come out and they are going to be in movement, do we call that as current? Because at room temperature, generally it is going to happen. The electrons are going to be in movement, but we will not be calling them as current. If you want to call this flow of material like electrons as current, then that should be in a particular direction. So if you're going to have a rate of flow of charges in a particular direction, we'll be calling that as current. Now in this also we'll be saying that whether it is going to be a huge amount of current or small amount of current. So whether the current is going to be higher in amount or less in amount will be decided by the number of electrons which is going to be flow. So if you're going to have more number of electrons, we'll be calling that as a large amount of current. If you're going to have less number of electrons flowing, we'll be calling that as the less amount of current. Why it has been represented as charges instead of electrons is nothing but there is a possibility for the positive charges also to flow. But most of the time the easiest one which could able to flow is nothing but electron. That is why more specifically I'm saying here that as the electron. And the one more factor what we have to worry about it, not only the amount of charge which is going to decide the current, the amount of time. That is, for example, within what time the amount of charges is going to flow, that will also decide. For example, within 1 minute, if you're going to have only one electron, that is not a huge current. Within a 1 second, if you're going to have 100 number of electrons are flowing, that will be called as a great amount of current, right? So time is also one factor which is going to decide the current. So by adding up them or by having a conclusion about whatever we have done with the previous slides, we can have the definition for the current over here. The current is nothing but the rate of flow of electric charges. The current is nothing but, I'm repeating, rate of flow of electric charges. What do you mean by this term rate? What do you mean by this term rate is nothing but if a quantity is going to get changed with respect to time, then we'll be calling that as rate. As charges are going to move over here, we are calling that as rate of flow of electric charges, and the unit for that is ampere. What do you mean by this term rate of flow of charges? I explained you already. What do you mean by this term ampere is nothing but the unit of charge is going to be coulomb. So if you're going to have 1 coulomb of charge which is going to flow within 1 second of time, so 1 coulomb per 1 second is going to be equivalent to what is called as 1 ampere. As it has been found by Ampere, we are giving that name to him, which is going to be the Ampere one over here, right? And in your book you will be seeing one more way of writing this as well, which is nothing but del Q divided by del T. What do you mean by this? What we have to understand from this is nothing but rate of flow of charges, which means that when, as you're seeing in as you have seen in the previous one over here, when time t equal to 0 second, you must be able to see only one electron, but when the time keeps on increasing, we'll be able to see more number of electron, right? So when it is going to be time t equal to 0, the time t equal to 0 is going to give you very less number of electrons. Or for example, for momentary, we will be taking that as 0. But when t is equal to 10 seconds, it is going to become the number of electron cross the particular circuit or particular wire is going to be 10 in number if you are going to take. Then what is the difference between this? You have that has been written as over here as charge. That is 10 coulomb of charge you can write. 0 coulomb and 10 coulomb, the difference is 10 coulomb. And when you're going to take this time over here, 0 seconds to 10 seconds, the difference is going to be 10 seconds, right? So the ampere what we are going to write here is nothing but 1 ampere. Okay. It's going to be 1 ampere. This is how this is being justified over here. And what is the one more thing you have to know is nothing but normally the ampere is a unit what we are using, but the coulomb is going to be the huge amount of charge. Generally we will not be having this much amount of charges flowing through anything. The amount of current flowing through normal materials will be normally given in terms of the milliampere, or it will be given in terms of the microampere only, as the amount of charges flowing through them will be very less in magnitude. And when you are coming for the flow of electric charges, as we know, there are two terminals called as negative and positive, right? If you are going to look at it, negative terminal will be having more number of negative charges, that is the electrons accumulated on it, and as the electrons are going to repel each other, the electric charges will start flowing from the negative terminal and it will be moving, that is it will be attracted by the positive, so it will be moving towards the positive terminal, right? This flow of, that is negative to positive flow of electric charges in a circuit is called as electronic flow of current. When it is going to be given for you as positive to negative flow of electric charges, that will be called as conventional flow of electric current. So there are two types of flow of electric current. One is going to be the electronic flow. One is going to be called as the electronic flow, in which you will be having the charges which will be moving from negative to positive. If it is going to be mentioned as conventional flow of electric current, then that is going to have a current flow from positive to negative as per the circuit what you are going to have. Okay, and this is how exactly a circuit work. Whenever the battery is going to be switched on, the electrons are going to be start moving from one terminal towards the other one. In the middle of it will be having the appliance which is going to receive the energy of the electron, and which is going to work, and the electrons will go back again, right? Now there must be one more question arise, which makes these bulbs to work. The electrons are getting in there and they are going out, they are not staying there, or they are not being consumed to make the bulb to work. So which makes this bulb to work is nothing but potential energy, or the potential difference we used to say. What do you mean by this term potential difference? Only we are going to do with this small example here. As I am saying it over here, when you are going to look at it, you could able to see a pizza shop and a delivery boy, and he is going to go to a house or a place where the pizza has been ordered, and he is going back. If you are going to look at it, the battery and the wire, the electrons and the appliance, all of them are going to be comparable. Here what is the pizza shop you are going to have, that is going to be equivalent to the battery. Battery is going to be the place where the energy is being supplied. That is, the pizza as a kind of energy what we are going to get, right? So the energy is going to be supplied, and the wire is going to be the pathway through which this energy is going to flow. But to carry this energy we need someone. That someone is nothing but the electron what we are going to have. So the delivery boy is going to be the electron. So electrons are already present in the wire, we have done it already. The electrons which is present already over there are in random motion. To make them to move in a single direction, that is towards the appliance, we need someone who is going to push them. That is what is the work of the battery over here is. So from the battery, the electrons are going to receive energy with which they are going to flow in a particular path, and they are going to receive the appliance, they are going to deliver the energy over there, and they will be moving back without energy to the battery again. Like the delivery boy, he will be taking the order from the pizza shop, and with that energy, that is with that mass in his hand, he will be coming through the pathway where he need to deliver it. When he is going to deliver the food, he will be getting the money back from it, but it will not be the same amount of mass what he is going to have. He is going to deliver that and he is going to get the money, and he is going to go with less amount of weight back to the shop again to refill him. That's the same thing the electrons are doing. So where the potential energy, or what do you mean by this, what is the potential energy, potential difference we are going to talk about here is nothing but he is going to get, like the electron is going to gain energy. For example, the electron is going to gain 10 joules of energy. I'm not talking about all the electrons, I'm just talking about only one electron. So one electron is going to gain 10 joules of energy from the battery. With the 10 joules it will start moving. So it's going to go through a path like this. When it's going to travel a path like this, for the traveling distance, it would have been lost a particular amount of energy. Let us have it, for example, as 1 joule. When it is going to get into the appliance, for example, it is a bulb what has been given, right? So to make the bulb to work, it has to spend a particular amount of energy. If it is going to spend 8 joules of energy in making the bulb to work, when this electron is going to come out over here, what is energy it will be having? 1 joule. So with that 1 joule, once again it will be going through the same pathway, and with a very less amount of energy it will be reaching back the battery again. Now it want to move again, means it need energy, so it will refill itself and then it will be coming back. Now if you are going to see it, when it starts over here, the energy what it was holding is going to be 10 joule, and when it is going to reach again back over here is going to be 1 joule. So what is the energy difference you are going to have here is nothing but 10 joule minus 1 joule, which is nothing but 9 joules what you are having over here. So this 9 joules, that is the amount of energy spent by the electron to make this appliance to work. That is what is called as the potential difference is. Could you able to understand? The amount of energy spent by the electron which is going to be utilized to make the appliance to work is called as the potential difference. The similar thing you are seeing over here, we are having a truck which is going to get loaded when it is going to be entered into the battery. The truck is like the charges what you are going to have. Either it can be positive charge or negative charge. Over here I am showing you the positive charge instead of the electron. So that is going to get loaded. When it is going to be loaded, it is going to come for the first appliance. A part of that is going to be used, and when it is going to go for the next appliance, the remaining part of the energy is going to be utilized, and the rest empty box is going to be moved through. So what is this amount of energy? That is the orange thing you could able to see. That load which is being spent by that will be read out as the amount of energy by the voltmeter. What is the energy it's spending? What is the reduction in the mass of that? That will be read out by the voltmeter what we have over here as the potential difference about each and every appliance what we are going to have. Could you able to understand it? So the same thing I'm showing you here. All these things are going to be taken as a battery, and if you're going to look at it, the green thing associated with them is the energy what they are having. So when they are going to start, they have the green energy, and when they are going to get into the appliance, they are giving that energy to it to make the appliance to work, and they are coming out as empty. So this 3 is going to be the energy what they have. When they are coming out 0. So what is the potential what they are utilizing over here is nothing but 3 joules. So this is 3. When it is going to enter, it is going to have the energy of 3 joules. When it's going to come out, it's going to have 0 joules. So each and every electron over here is going to spend the energy of 3 joules, which is going to be taken as the potential difference over here. Hope so you could able to understand, right? The similar thing I try to show you off here. So the potential difference is going to be the amount of energy required to move or take a charge from one point to another point of the circuit. As you're seeing here, the charge is going to start from one point. So the charge is going to, for example, it's going to start from here. It's going to start from this point, and it's going to move through, and it's going to come back to another point. So to move a charge from one point to another point of a circuit, more precisely it would have been given in your book that the amount of energy required to move a unit positive charge from one point of the circuit to the other point of the circuit is called as the potential difference. Could you able to see this? Difference, because each coulomb of charge has a different potential energy either end of the battery. So as it is going to be defined as the amount of energy spent by the charges. The similar thing we are writing as the equation over here. Amount of energy can also be written as amount of work, because what is the energy we spend will be given by what is the work we are going to do. So the work done by the charge is going to be called as the potential difference. Work done or the energy will always be measured in joule. So if a charge is, if 1 coulomb of charge is going to spend 1 joule of energy to move from one point to another point of the circuit, then we'll be calling that as 1 volt. It is named after the person or the scientist who found this. Okay, could you able to get this one? Now what is the next thing we'll be doing is nothing but resistance. Before that, you must be learning about this term as well in the other chapters. That is electromotive force, EMF. What is the main difference between electromotive force and potential difference? Both of them will be saying that as charge. But what is the main difference? Try to understand. If you are going to take a battery or a shell, it's going to work based on a chemical reaction. That chemical reaction makes the charge to be stored. So because of which chemical reaction, the chemical energy is going to be converted into electrical energy. That is, for example, if you're going to take a battery, carbon battery, the normal batteries, cylindrical batteries would have been seen, right? We'll be having a carbon rod inside it, and we'll be having the powder electrolyte around it. So because of the chemical reaction happening between them, the charges which is going to be stored over there will be having a higher amount of energy associated with them. That conversion of total amount of chemical energy into a kinetic energy, electrical energy, is called as the electromotive force. That is between the two rods, positive and negative. How many of you remember the electrolysis process? So the total amount of energy difference between the positive and negative rods, that is cathode and anode, that is what is the electromotive force to move it from one the electrode to other one. But the potential difference is going to be the amount of energy spent. Most of the time the amount of energy spent is going to be in terms of the heat energy. So when the electric charges are going to be flow, that is the electrical energy is going to be transformed to an appliance. What is the amount of energy is going to be lost by it in terms of the heat energy? That is called as the potential difference. But both of them will be taken as with the same unit only. Okay. And what is the next thing I told you? The next thing what we are going to do about this is nothing but resistance. As you are seeing over here, the electron flow is going to be opposed by something. So it could be anything. It may be the nature of the wire, or the material by which the wire is being made up of, with the dimension of the wire, or the surrounding thing. It may be the surrounding temperature, or it may be the surrounding pressure what we are going to have. There are so many factors which could able to act as a resistance. So in general, what is resistance is nothing but which is opposing the opposition of the flow of the opposition of the flow of electron. If you are going to have, all of them will be called as the resistance. All of them will be called as the resistance. But this resistance, you could able to see here, the resistance is an electrical quantity that measures how the device or the material reduces the electric current flowing through it. So the amount of electric current flowing through the material is going to be resisted. That will be called as the electrical resistance, and it's going to be given by the unit ohm. Once again, it has also been named by the scientist who found it first. This electrical resistance will be based on so many things I told you. Out of that, we are going to do one thing, that the electrical resistance is going to be based on the dimension of the wire what we are going to have. Either the wire is going to be lengthy, or it is going the cross-sectional area of the wire is going to be more or less. That will be deciding the factor. That's what exactly we are seeing. Suppose if you are going to have a wire which is going to have a higher length, you could able to see that more number of electrons are flowing through it. If it is going to have a shorter length, less number of electrons are flowing through it. Does it mean that you are going to have a higher amount of current flow through a lengthy wire? No. Why it is, or how you can able to remember this is nothing but just remember, it's going to be your favorite movie. You want to go and watch it out in theater, and we are 20 years back. Okay, we are going to be 20 years back. That is, we don't get tickets normally. So what we have to do is nothing but we have to stand in a queue and we have to get the tickets. So imagine this length of the wire, what you're going to be as the length of the queue where you're going to stand. All these electrons are going to be each and every person. So if the first person is going to move to the counter is going to be the battery. The first person has to go to the counter, he has to get ticket, then only he will be leaving the way for the other one. So if the length of the wire is going to be more, the number of electrons need to be in the queue will be very high. But if the queue length is going to be short, the first person will get it easier, and the second person and the next person will also get it with a lesser time, right? So the amount of resistance in reaching the the battery will be less when the length of the wire is going to be less. But when the length of the wire is going to be more, the queue will be more. One by one only the electrons could able to move, which will make the increase the resistance for the electron flow. That means that if you are going to take the resistance of the material and the length of the material associated with that, the length and the resistance, both of them are going to be directly proportional to each other. If the length is going to be more, then the amount of resistance associated with that also more. Both of them are going to be directly proportional to each other, right? And what is the next factor is nothing but area of cross section. As you're seeing it over here, if the area of cross section is going to be less for the wire, then the number of electron flowing through that is going to be less. But if the area of cross section is going to be more, at a time you could able to have 3 electrons which is going to come. Over here only 1 electron, right? So if the more area it is going to have, more number of electrons which will be flowing through it. That means that if the area is going to be more, the amount of resistance will be less for the electrons to flow. If the area of cross section is going to be less, then the amount of resistance for the electron to flow through that will be more. Yeah, so by concluding them, we are having the formula over here. The length of the wire is going to be directly proportional. So if you are going to combine the two equations what we have written already, resistance is directly proportional to length and it is going to be inversely proportional to the area. Always to take off the proportionality, we will be writing a constant. That constant is nothing but the resistivity over here. This resistivity is called as specific resistance as well. What do you mean by this is nothing but, if you are going to, for example, you have it over here, right? So the material what I have taken over here is going to be having the length of 1 meter and the area of cross section of that as 1 meter square. At the time, in the specific material, what is the resistance present? That is equal to, that is 1 by 1, that is equal to resistivity or the specific resistance of the material. So the resistance is not constant for the material, but the resistivity for a particular material will be constant. Okay, what is the next thing we are seeing over here? You could able to see something. Yes, 3 scientists, as well as there is a term which is named as ohm, right? So as you're seeing over here, ohm is a person who's trying to control the amps and volt is the person who's trying to push it out. So this is what is our Ohm's law, darling. The connection between the voltage, ampere and the ohm is called as the Ohm's law. Why do we call this as Ohm's law is nothing but ohm is the person who found about this relation and he gave it. We all know that voltage is going to be the amount of energy given to the electrons to get into motion or get into flow in a circuit, right? So this volt is going to be the pushing energy for the electron. As you're seeing here, the electrons will get pushed by the volt. But the resistance is going to be the one which will not allow this. It will be opposing the flow of this electric charges. So what is the relation between them is being given by ohm as the voltage and the current, both of them are going to be directly proportional to each other, but they are going to be directly proportional to each other by a factor called as resistance. So the resistance in a circuit will be deciding that what is the amount of current and voltage is going to flow through it. So V and I, both of them are going to be directly proportional to each other, but that proportionality will depend upon the resistance what they are going to have in a circuit, right? So voltage will be given by V is equal to IR, right? You can remember this with the help of a small hint as well. I would have been said about this or you would have been heard about it already. V represents, for example, vegetarian, and IR we could able to say it, right? So I is always used to take vegetarian food only. That way also you can remember this equation where V is directly proportional to I. Whenever two quantities are going to be directly proportional to each other, then obviously they are linear to they will be giving us the linear graph. So the graph what we are going to have always be a straight line. You could able to see it over here, right? And the straight line, if you are going to take for the straight line at any point, if you are going to take a slope, the slope will be given by y-axis difference divided by x-axis difference, which will be I by V. V is equal to IR. Then I by V, if you are going to have, what you are going to have? I by V from this circuit, what you are going to have? 1 by R. Am I right? So 1 by R is nothing but the conductivity of the material. You could able to get. So the slope of that will be giving you the conductivity what we are going to have over here. what is the next step we are going to do is nothing but we are going to do something called as current density. What do you mean by this term? Current density is nothing but how much amount of electric charges are going to flow within the given time is called as current, but through the particular area of cross section within that same time how much amount of charges are going to flow is going to be called as the current density. That is what is the amount of charge you're going to have over the area is going to be called as current density of that particular area what we are going to have. So how we are going to do that is nothing but, as you're seeing over here, we know that very well, I is equal to V divided by R, and R in terms of dimension will be given by rho L divided by A. Now if you're going to look at it, I, that is I is equal to V, the the R value we are substituting it over here, right? So when I'm rearranging it for the I by A, amount of current flowing in the given area. So what I'm exactly doing, if you're going to do the reciprocate of that, what you'll be having, VA divided by rho L is equal to I. So I'm just taking the I down over here, which will be giving me this equation. So V divided by rho L, right? So this V divided by rho L, when you're going to write it, we all would have been learnt about it in from our first chapter. The potential gradient we will be given by the electric field into the length, right? Length of the conductor what we are going to have. So V by L will be given by what then? E. So we are substituting the V by L as E over here, and 1 by rho, inverse of the resistance, will be called as conductance, and the inverse of resistivity is called as conductance. So conductivity. What do you mean by this? Resistance we know, which opposes the electric flow. Then conductivity must be how far or how easily the electron could able to flow. That is why both of them are going to be inversely proportional to each other. Sigma is the conductivity and the rho is going to be the resistivity. Both of them are going to be inversely proportional to each other always. So the expression for the current density over here is going to be J is equal to sigma into E. You could able to get this, or you could able to say that as well. The J can also be said as I by A, amount of current over the area, or you can say that conductivity into amount of electric field what you're going to have over there. Yes, so what is the next thing we are going to do is nothing but drift velocity or drift of electron and the origin of resistivity. What is this is nothing but it's a very simple stuff. That is, I told you when at the room temperature we are going to talk. In the room temperature itself the electrons are going to be in motion, but the energy is available for them in all the directions, so the electron flow will be random. What we are going to have, the electron flow which is going to be random. If the electron flow is going to be random, then you will not be calling that as the electric current, I said, right? So to make the electron to flow in a single direction, we need to supply an external energy. That is going to be the electric field what we are supplying. Generally electric field, when we are saying, that is going to be the negative to positive thing what will be sending, right? So the negative potential if you are going to send through a material, then the electrons are going to be the one which will get repelled by the negative. Yes. So if the electrons are going to get repelled by that electric field what you are supplying, always the electrons are going to be drifted is nothing but they are going to be pushed or moved towards. The electrons are going to move in the opposite direction of the electric field which is being supplied. That is what is going to give us this drift velocity and the drift of the electron. Drift is nothing but the electron flow in a single direction or in a particular direction with the help of the electric field what is going to be supplied to it. The electric field what is going to be supplied to that will be called as the drift of the electron over here. So what we will be doing with that is nothing but the similar stuff, which is nothing but we are going to have a flow of electrons over here. So I'm going to have a electric conducting material. The conducting material is going to have a few number of electrons associated with that, as well as it is going to have the electric charges as well associated with that. That electric charges are going to get into flow with the help of the energy what is being supplied to them as the electric field. So if the electric field is going to be supplied in what direction, I said if the electric field is going to be towards the right, then the amount of electrons flow will be in the opposite direction, which is going to be taken in the left direction, right? So we have to combine that only over here. What is that combination we are going to have is nothing but, could you able to see that over here now? Yes, the amount of electron flow you could able to see, it is going to be in the random direction over here. But when the electric field is going to be supplied over here, as you are seeing, the electric field will be towards the left, means the amount of electron flow will be in the right direction. As you are seeing over here, the electrons will be drifted towards the right if the electric field supplied is going to be in the backward. Initially there is no electric field, the electrons are not have drifted towards any direction, they are having a random movement, right? So as per that, if you are going to write the energy over here or the formula for that over here, as you are saying here, what will be writing, that is normally the force on any of the material will be given by F is equal to ma. The electric force will be given by the formula F is equal to QE. Over here we have taken the charge of the electron, so it's going to be minus E instead of Q, and we will be having that as EE, right? So F is equal to ma and F is equal to EE. That means that with the velocity when they are going to move, that force and this force must be equal to each other. That means that ma must be equal to minus EE. Then the acceleration of that will be given by minus EE divided by m. That's what the exact thing you're seeing over here, right? So as you're seeing over here, the acceleration of this electron in the direction will be given by minus EE divided by m, right? When we are trying to talk about the velocity, generally the velocity will be given by the formula. What is the formula for the velocity? Displacement over time. Let us look at it in terms of the acceleration. Acceleration will be given by velocity, change in velocity over time. Then velocity will be given by acceleration into time. That's the exact thing we have over here. So acceleration has been replaced by minus EE divided by m into time. The change in time we have written over here. But this change in time we are going to write that as over here as with the another term which is going to be tau, which is called as the collision time, which means that when the electrons are going to start flowing, they are going to be in movement. That means that they are going to get into movement without colliding with another electron. There is a possibility for them to get collide. So if the electron is going to start moving, if it is going to have a time before, like what is the time it is going to have between two collisions, so it's going to start from here, it's going to move towards this way. For example, if I'm thinking without colliding this, how long it could able to move, that is what is called as the collision time what we are going to have. That has been represented by the term tau, and that's what's the thing with which we'll be replacing this now. So the delta V, when the delta t is going to be taken as tau, then the delta v can be said as the drift velocity, the velocity with which the electron is going to get into movement. So the drift velocity will be given by minus EE divided by m into tau, where tau is the collision time and Vd is going to be the drift velocity what we are going to have over here. Could you able to understand this? So what is the next thing we'll be doing is nothing but how these electrons are going to be get into motion. That is with the supplied electric field, how these electrons are going to be in movement. Mobility is nothing but it's representing the movement of the electron, right? So that movement only we are going to do with the next part of this. The mobility will be decided by the electric field, I said. So the similar kind of expression only we'll be having for the mobility as well. Mobility will be represented by the term mu. What term we will be having? Mu. Please make a note about this, whatever is on the board, as well as what I have written over here. You may forget this force, how these forces are going to be connected and how we got this equation. Suddenly we got this over here, so you may have a confusion. So please note this down immediately. Then I'll move on to the next stuff over here. I'm just passing it for a few seconds so that you could able to notice it, and then we'll be able to get into the next one, right? So as you are seeing over here, what is the definition for the relaxation time, or which I told you that as the collision time, right? So that is the definition what you're going to have for the mobility over tau over here. The quantity tau is called as a relaxation time, right? Now we are going to replace this drift velocity to the current density. How we are getting this equation? If you think, what is the formula for the current density? We have done already. J is equal to I by A, or you could able to have that as J is equal to sigma E, right? So we will be having the value of that as J is equal to minus NE into VD. How we got it? That's what's the same thing. You could able to have a look over here. So the sigma value what you're going to have is going to be given by this, and what is the value of the drift velocity? We have done it in the previous slide. That has been substituted over here. As you are seeing it over here, the conductivity of that is going to be written with the help of the formula what you are going to have over here, that is NE square tau divided by M. That is how sigma into E you are going to have. So the sigma must be represented by NE square tau by M and into E, as you are seeing over here. Then what is the next step we will be having? With the sigma, what is another thing we could able to connect is nothing but resistivity, I told you, right? So that's the same resistivity what we'll be doing over here as well. So if you're going to have the value of the sigma as NE squared, that is this value, then the inverse of that M divided by NE squared tau will be giving you the resistivity value over here, as both of them are going to be related to each other. Okay, so the mobility is also going to be related to that as well. I told you the same way we'll be writing the mobility of that as well. Okay, so what is the next thing we are going to do is nothing but we are going to just conclude all of them. What are the things we have done with today's session? What is electric current, what is voltage, what is resistance, what are the factors affecting them, and what do you mean by the term current density, what is the formula for it, what is resistivity, what is conductivity, what is the relation between them, right? So the rest of the things will be continuing with the next class. What is the homework for today's session is nothing but exactly after the mobility you will be having the book example which is going to be 3.1 and 3.2. so you're going to do that 3.1 and 3.2 in your homework notebook. Hope so all of you having your boardwork notebook as well as homework notebook, right? So you're going to do these two problems in your homework notebook on the problem side, and whatever the other steps we have done now, all of them should be noted down in your homework notebook as well. So you're going to draw a mind map for whatever we have done in today's session as well. So in the next class I'll be coming out with a mind map. You can check with that with yourself. Okay, so the mind map for the topic what we have done, and these two problems are going to be the homework for today's session. Is that is clear for everybody whatever we have done? If you have any doubt, please leave the text in the chat box. Thank you, children.